Okay, so let us start. Today we'll see a new unit number 3, which is actually microwave passive components, and the last unit will be the microwave active components. So in this unit, we will see the number of passive components used in RFL microwave engineering, and we'll try to find it out its working mechanism and associated mathematics, and be a number of things actually. So we'll be talking about the very basic one, fundamentals, and we'll see some of the things. Like here you can see on the screen there are different the passive components are there, like attenuators are there, ferrite based components are there, correct. Digital attenuator is there. So similarly other things are also there, like phase shifters. um, so many things are there. So how the things are working, like the basics and all the things, if we want to understand, correct, we should have some fundamental thing, like what we have, like transmission line, knowledge of the transmission line, okay, knowledge of the waveguide, correct, and some the mathematical background, correct. So once we have these things, we can understand the working of these components, okay. So let me tell you first the overview, what we are going to study in this unit. Okay, so particularly this is unit number 3. Okay, this is passive components. Fine. So what we'll study actually in this unit, that first we'll see the terminators. Or variable shorts. Okay, so in this we'll see the match lot for the waveguide. Okay, so like in our previous classes, what we have seen, we are using short, load, matched, any kind of loads, and we perform the several analysis of that. Correct. Now here we'll see that how the construction of these variable shorts, termination, match load, okay, and particularly working as well. Okay, so separately we will be discussing all those things, and these are very important thing you will be having in a lab, that variable short circuit. Second, we'll see the attenuator. Okay, and in this we'll see the rotatory mechanical attenuator, rotatory attenuator, uh, like variable register. Have you used actually in a lab? So in basic electronics lab, we use this thing so we can vary the resistance value by rotating that knob. Okay, and another is attenuator is based on the electronically controlled attenuator. Fine. So electronically controlled attenuators are really needed actually, because it is difficult sometimes in a remote location if you want to change the attenuation level, correct. So means from the control room itself you can manage the attenuation level, correct. Now the third is the phase shifter. Okay, so many times in these things, RF and microwave systems, we require to control the phase shift, and the phase shift actually controlled by the phase shifters. And basically there are two kinds of these things. One is the rotatory phase shifter, And second is we have electronically controlled phase shifter. Fine. Now another important component is that power divider and directional coupler. Huh. So this is really needed actually, because sometimes, okay, you require some amount of power should go in one direction and some amount of power is going another direction. So for that we require power dividers, maybe equal power division, maybe having in some ratio. And similarly, like directional coupler is one of the key elements in a microwave engineering, and based on that many instruments was proposed later on. So directional coupler actually basically if you require some there is a coupling port, there is a through port and isolation port, and there are 4 port device actually, and we can manage such in a way that what we want the through port and the couple port, and in this way this could be also used to record the reflections also of the devices. Correct. So this is one of the very important thing, and somehow we can also find it out the S parameters out of these directional couplers, different kind of directional couplers actually. Okay. So the next is the power divider. Okay. So like power divider and directional coupler, if you see, so basically we'll see in here the properties of the 3 port network, the T junctions. Okay, and we'll also see the 4 port network. As I told you, directional coupler. In short, we are calling as a DC, and the 3 dB hybrid coupler. 3 dB hybrid coupler basically used for this thing half power divider, where we require the half power in output ports. Correct. And the last one is we'll see that microwave ferrite devices. The fifth one is microwave ferrite devices. Fine. Here we'll see gyrator, then isolator, and circulator. It's very much important in these things. Circulator is one of the very important component in a microwave device. It stops actually the backward propagation in some applications. Okay. Now, so I'll start with the different kind of domination and all those things. Correct. And we'll continue step by step. We'll try to cover all those things. Okay, but before that, I would like to tell one thing that we have seen the number of passive devices and circuits actually for different applications. Now, how you are going to realize these things? Okay, how these 5 major components. Okay, there are others also. How you are realize these technologies? So there are technologies involved like a waveguide. Okay, using the waveguides, we can develop these things. Second is we can develop these things by coaxial transmission line. we can develop with the microstrip technology. That's very important nowadays, and strip line in some of the application. Fine. So this is the thing actually. So if I talk about the terminations first, okay. So as I have shown you the first slide, so this is one kind of termination actually. Okay, variable termination, like variable short kind of things, correct? So here we can shift the location, like we have seen in some problem, okay, so where we have to keep the short so that we can control the minimum location, okay. So this is for that purpose. So let us try to understand the working mechanism and the construction of the variable short, correct. So first, if we're talking about the terminations or variable short, correct. So there are two type of waveguides and transmission line used for these terminators. One is match load for the waveguide, and the second is variable short circuit. Okay. So particularly if I talk about the first one, correct. So it actually involves like basic theory or basic idea actually is uh, depends on the lossy wedges, slabs, and the tapered resistive guards. Correct. Means what I'm saying. Let's say if I try to make a waveguide kind of things. Okay, I'll try to do these things. So what's happened actually? So there's a slope actually. This slope. Okay, inside this. Okay, inside there's a slope actually, and this slope is made of some material actually. And the another case is that you have a tapered register card. Okay, means what I'm saying that there's a tapered card inside. You try to fix it. Okay, this kind of tapered card is there. Okay, this is a resistive card. Okay, and here we are introducing a lossy wedge or slab. Okay, which can absorb the things. Fine. So the thing is, all incident power absorbed. Okay, and so should I write actually absorbs all the incident power. Yeah, like we are talking about the match load. When it is called as a match, it will going to absorb all the thing. Nothing will be reflected back. Okay, so the criteria is that we have seen that we can do with a resistive card or we can also do with the lossy slabs. Okay, so it absorbs all the incident wave. First, that the termination of the line in its characteristic impedance. Second, tapering of the lossy material minimize the reflection. Third point is an overall length of one or more wavelength is usually sufficient to provide the required matching. Okay, so the thing is like, this is all the things I have written with this figures actually. So here the first thing is the lossy slab. Okay, and if you see here, there is a slope here. The slope is the reason actually because there is a gradual change in impedance, and hence we are matching the circuit. Whereas in this case, we have a resistive card. It is the nature like resistive card is made of the carbon composite. Okay, that can be used for absorbing these EM waves. Okay, so this is very well known actually. So we are keeping this thing, but these match loads are the fixed kind of things. Okay, they may be working at the certain frequency or maybe a band actually. Correct. Now another thing is that like this is the fixed kind of things. Now let us talk about the variable short circuit. Okay, so variable short circuit, what is that? The first point, termination for reflecting all the incident power. Second, phase of the reflected wave is controlled by changing the position of the short circuit. Okay, so like these two things are this variable short is characterized actually. Now, if you talk about the construction of these things, okay, so the construction is not a very difficult actually. Like we can understand like there is a waveguide kind of thing, maybe circular or this kind of thing. Okay, and after that you have a scale, a micrometer drive. Okay, after that you have the micrometer drive. Fine. Okay, so this is you can rotate. Fine. And here this scale, this micrometer drive actually connected with just a minute. Connected with a sliding plunger. Okay, this is connected with a sliding plunger, and the thing is it having the sufficient space between the walls and this thing so that it can rotate. Piston kind of situation. Okay, there's a piston kind of situation. You can understand like that. So this is what this is sliding plunger. Okay, and this is of course this is a waveguide. Okay, so inside that there is a movement of this plunger. Okay, and we can expect the required this thing. Okay, so the thing is, like in a waveguide, a block of copper, okay, this plunger may be a block of copper or some other conductor fits into the waveguide. Okay, and this could be, the position could be controlled by the micrometer drive. Okay, here you can see this is a micrometer drive and we can rotate. I hope you use the this things uh, this kind of micrometers in the lab in 10+2. So in that case, when we are tightening the things, so we are increasing the length. It means it is going this side. Okay, if we are releasing, so it is coming back to here. Okay. Okay, and there's a one more thing you need to take care. The electrical contact between the sliding block and the waveguide wall is not like it should be some gap actually. Means there's a not more gap actually, otherwise leakage problem will be there. But there is sufficient gap so that the thing plunger could be moved forward and backward. Okay, now the thing is we can realize actually, but when like that is okay, fine, okay, with this actually this device, the working and other thing is mechanically we can understand. But if let's say if I'm asking that, can we make a equivalent of this? Okay, can we realize this whole system in an equivalent circuit form? Okay, can we do? Yes, definitely. It could be more justified as an electronics engineer. I can visualize properly. Okay, so the picture is clear that like this is a variable short, so sliding plunger must be of the copper or some other conducting material, and we are moving the position of the short. Okay, so as I told you, the perfect electric conductor, okay, could be used for these things, variable short and all. So let us try to understand this thing, the circuit of this thing. Okay, this variable short. Okay, and there is a one more thing actually, that due to the power leakage, there is a power leakage actually. This because of this gap and all. So reflection coefficient is less than unity. Now let us talk about its equivalent circuit. Okay, and later on we'll see that how we can improve the short circuit. Okay, but first we'll try to understand these things. Okay, so I'm going to make this thing. So this is one section of lambda by 4, and this is ZS. Okay, so this ZS is actually, this is impedance corresponding to the actual short circuit. Fine. So this is we called as a two section quarter wave transformation. Okay, so this is, let's say the impedance is Z1, this is Z2, and this is ZS. Correct. And here we have the lambda G by, sorry. So this is lambda G by 4, and this is also lambda G by 4. Okay, and this is, let's say if from here you have seen the impedance of Z dash S. Okay, so now if I ask you to find it out here, if you see the impedance from this side, so ZS dash will be equal to Z1 over Z2 the whole square Zs. And if you see from this side, okay, so this is, let's say Z in 1 is Z2 square by Zs. Okay, now I think this picture is clear, because if you see from this side, so this is lambda g by 4. Okay, so we already have the quarter wave transformation. Okay, so for the quarter wave, we know the relation between the input impedance, characteristic impedance, and load impedance. So this is given by this. Now, like if this is the Z in here at this location, again you have the lambda g by 4, correct? So you can easily find it out Z as this. Okay, so we can find it out these things. Okay, this is the impedance seen at the input is this, correct? So like here, this is the that impedance corresponding to the actual short circuit. So now you can manage actually the ZS dash actually seen at this point. Fine. Now if Z2 is greater than Z1, okay, so what will happen, that the quality of short circuit improves by a factor Z1 over Z2 to the whole square. Okay, why? If Z2 is greater than Z1, so the overall value will be less, and that is actually we require. Are you getting this thing? Why? Because we need to realize a short circuit. Okay, and for the short circuit, it should be minimum. The impedance should be minimum. Ideally, should be 0. Correct, but it should be minimum. Then it will be really good. So we need to manage like this situation: Z2 greater than Z1. Okay, Z2 greater than Z1, and Z1 and Z2 you may correlate actually with this. Okay, so the thing is how we can further improve, these things. So for that actually, if somehow we can use a waveguide based choke type plunger. Okay, so this could be improved actually. So let us try to understand first its construction, and then we'll comment over these things. Okay, so the construction is almost same, but there's another plunger here. So this is a waveguide again, fine, and this is a metallic plunger. Okay, and again here we connected with a small one. This is a small one with the previous one, I think. And the same thing at the other side, that we have a micrometer, this thing scale. Fine. Okay, and let us define some of the things. This is our waveguide dimension. All the waveguide dimensions are, this is B, correct? And of course this is Z dash dash, this is ZS, fine. And fine. So this is lambda g by 4, lambda g by 4, what we have seen in a previous circuit as well. And this is what? This is B2. And this gap is B1. Fine. So this is the almost we can realize the situation what we have seen actually here. Okay. The same situation, lambda g by 4, lambda g by 4. Okay. So because we know these things that if Z2 is greater than Z1, okay, so the quality of the short circuit could be improved by Z1 by Z2 to the whole square. Okay, so this is particularly applicable at the single frequency, first of all. But there's a limitation actually. Uh, However, we can make it broadband, we'll see. And one thing is that the width of the plunger is made uniform. Fine. With height being non-uniform. So this is actually by this way we can alter the impedances. Okay. So now we can relate a very important relation that Zs dash is equal to B1 over B2 Zs square. Fine. It means that if B2 is very greater than B1, okay, practically how you will realize I'm trying to explain this thing that B2 is greater than B1. B2 means this value and this is value is greater than. So, or we can if expect this in B2 is equal to B1. Okay, so you may guess actually 10 times of 10 times of B1. Okay, so like if you are putting this is 1 by 10 to square means 1 by 100. Okay, so now whatever the ZS actually, okay, the ZS is this things, the plunger. Like similarly in this case also, like we have a single plunger. Okay, so from here we are expecting ZS. Okay, so this ZS ideally should be very less or zero actually, correct? So now the thing is we try to improve this. How we can improve actually we have seen by this equivalent circuit. So here you can see this is ZS actually offered by the plunger, and then after we added Z1 and Z2. So in this way we can improve. Okay, and this is actually this circuit actually critically relies by like this. Okay, so here we included another pad, okay, connected with this plunger actually, and there is a gap actually this thing, and this gap actually is controlling these impedances. Fine. And let's say if you are managing this gap and this gap with this ratio, so you can improve the overall impedance 1 by 100 actually. Okay, so in this way you can drastically reduce the impedance, and hence you can realize the perfect short circuit. Correct. So this is one thing actually. Still in a lab actually, if you go, you will see we are using this rotatory based kind of variable short. Okay, but the improved version is there. It's working at some frequency bands, not a single frequency. Correct. So this is all about the variable short. Okay. Now, like another thing is the attenuator. Okay, so attenuator is really very important actually, because when we are performing the high power application and other thing, so sometimes it is needed that some instrument needed that means that power is another thing. Like we can definitely this power and other things we should analyze, but it's very important for us that phase actually. Okay, phase is another criteria. So sometimes at some instrument it is difficult to handle this high power. So what we can do without actually without destroying the originality of the signal, correct? We are just attenuating the power only. It is going to affect the power only with some factors, and then we are feeding to the instrument so that the instrument is not going to damage. Okay, so this is one application. Other applications are also possible, like mixing of the signal. If you want to mix the two signal uh, with certain power level, okay, you can control with this attenuator. So attenuator is also coming with a mechanical attenuator as well as the electronic attenuator. There are various use actually, various use, like when you are working with the amplifiers. Okay, so like you want to measure the gain versus power. Okay, so in that what you will do, you have to you have to feed your amplifier, correct? First the do the biasing, then after the RF input signal, then RF output. Now, if you're going to analyze, let's say on the spectrum analyzer or another thing, and the spectrum analyzer or the power meter having the limitation that it can accept not more than 10 dB, okay, and if the amplification factor is very high and the output signal is more than 10 dB, so your power meter could be burned, okay. This could be going to damage, okay, by this output signal. So for that actually we supposed to put an attenuator before that, means before your instrument, so that there is a less chances to damage this thing, and you can control and you can see properly. Because let's say if the output signal is going to have the 20 dBm, okay, and if you introduce 15 dB the attenuator, so you will be observing the signal of 5 dB on the machine, okay. So immediately you can predict, okay, the attenuator value is 15 dB and 5 dB actually I am observing on the instrument, the total signal is coming out is 20 dBm, fine. So in this way actually the analysis could be performed experimentally without damaging the instruments, okay. So particularly if you talk about the attenuators, so they are providing the fixed or variable attenuation, as I told you. And almost the simple idea is here, like what we have seen earlier, that it consists of the thin tapered resistive cards, okay. It consists of thin tapered resistive cards, okay, in a waveguide, okay, through slots or other things, okay. So this could be done actually. Fine. The attenuation level could be controlled by the changing of the depth of the penetration inside the waveguide. Another point. Okay. So the thing is, there are disadvantages also. Okay, and the disadvantage is like the output is attenuated by the reducing the coupling between input and output guides, and not by the absorption of the incident power. Fine. So the thing is, we will start from the rotatory attenuator, which is the most satisfactory precision attenuator actually. Still we are using in a lab, correct? But most of the time you will see in a lab that we have a fixed type of attenuators, okay, where we are fixing like 20 dB, 10 dB, 5 dB like that, okay, fine. So we'll see these things, okay. So I'll suggest you please check the rotatory attenuators. Okay, so the idea is almost same actually. The idea is almost same what we have seen, the tapered card and all, but there is a mechanically the things are different. Okay, so we'll be talking about in the next class, correct? So I can see that students are very less, correct? So I'm expecting that next class will having the good number of the students. Okay, so we'll be starting the rotatory attenuator, it's working, and the construction and other things we will be checking. So if you have any questions regarding this thing, so you may discuss with me. Okay.